Hello everyone. In this video we are going to discuss about the next concept, which is the packetization in the packet switching, or you can say the packetization in the network layer. Now, as I told you, in terms of switching, there were two types of switching majorly, which is the packet switching, and second one is the circuit switching. Now, in case of circuit switching, all the data packets has to follow the same path, because we not be having any other path between the sender and the receiver. But in case of packet switching, every data packet can take a different paths. What does that mean? Assuming that this is a sender and this is the net receiver, between sender and the receiver there may be multiple paths that are present, like this. There may be any number of paths between the sender and the receiver, like this. Okay, now if the sender is sending some data packet to the receiver, now that data packet can take any path. It can go through this path, it can also take this path, or any path it can take. Now this path can be decided according to the algorithm that we are going to use, or you can say it can be the routing algorithm which decides this path. Now this routing algorithm, there is a lot of research has done on this routing algorithm. Now most of the time research may be based on efficiency of the network, it may be based on reliability of the network, and so on. So the packet can take any path. Now if you are sending multiple packets and any one of these packets can take any path, now it is important for these packets, to know the destination address, as well as the sender address, because if in any case the packet is not delivered to the receiver, then at least the packet should notify the sender that I'm not delivered in any way, or what may be the reason I'm not delivered. So the packet should contain the destination address as well as the sender address. Therefore every packet here will be having two parts. If I just zoom in this packet, now this entire packet, it may be having two parts. Number one is the data that we want to send plus some header. Now this header contains the address and other information. Address, for example, what is the destination address, as well as what is the receiver address, Okay, so the packet is having data and the header, which header is having the destination address, receiver address, and data is the data that you want to send. Now this thing is called as packet switching, that where the packets can take any path through the network. Now this packet switching, there's something called as packetization in the packet switching. What is this packetization? It says that if we have a packet which can be a bigger packet, assume it is a packet of 1 megabyte, that means you want to send 1 megabyte of information, then you can divide this packet into smaller units. Let us say it is 2 KB, every smaller unit is of 2 KB, and so on. Like this you can divide. Now if you are dividing this bigger packet in a smaller packet, then what will be the benefit of that? What is the benefit? Will there be any benefit of this or not? And in what cases can you say that there will be a benefit? In what cases can you say there will not be any kind of benefit? Now imagine the scenario like this, that we have a sender and we have a receiver, okay, and we want to send a data packet. Assume that the data packet, or the data that we want to send, is of 1000 bits. I'm just taking these numbers for simplicity. I could have taken, bytes, I could have taken anything, but I'm just taking these numbers for simplicity so that the calculations become very easy. And assuming that the bandwidth of the network is 1 kbps, that is 1 kilobits per second. And let us say the header that we are using is of 100 bits. What does it mean? It means that every data packet that we'll be sending, it is having two parts. Number one is the data part and second one is the header part. And we know that the data is of 1000 bits, and therefore the header here given is 100 bits. So if the data is of 1000 bit and header is 100 bits, therefore the size of the entire data packet will be 1100 bits, like this. Now between the sender and the receiver, we may be having any number of routers in the middle. Now the sender want to transmit this data packet to the receiver, which is having data plus header. Okay, so first of all the sender has to transmit this data packet to the transmission media, then it will propagate here. So let us say the propagation time is TP1 between the sender and this router 1, assuming this is the router 1, this is the router 2, and this is the receiver. And then in the router the packet will be stored, again it will be transmitted. So this is the transmission time T1, this is the transmission time T2, and again from here to here we have the propagation time as P2. And then again on this router the same data packet will be transmitted, assuming the transmission time this is T3, and from here to here the propagation time is TP3. Now for simplicity purposes I am assuming that the bandwidth of the entire network remains constant. For simplicity, assumptions that I am using, the bandwidth of entire network is constant. So what happens if the bandwidth of the entire network is constant? Then this transmission time T1 will be equal to the transmission time T2 will be equal to the transmission time T3. All these transmission times will be the same. And what will be this transmission time? As you know, transmission time is the size of the data packet, divided by the bandwidth of the network. And for this particular case, the size of the data packet is 1000 plus 100 bits divided by the bandwidth of the network, which is 1 kilobits per second. 1 kilobits per second. So it will be 1100 divided by 10 raised to power 3 bits per second. So that is going to give us 1.1 second. Okay, so the transmission time in every T1, T2, T3 will be 1.1 seconds. Therefore the total time for transmitting this data packet, will be transmission time T1 plus propagation time P1 plus transmission time T2 plus propagation time P2 plus transmission time T3 plus propagation time P3. So I'm removing all the unnecessary informations like what is the queuing time and all this other information, just because for us the transmission time and propagation time, only these two things are important for this particular case. So the transmission time T1 is going to be 1.1 second plus, let us say the propagation time is same TP1, transmission time it is T2 is also 1.1 second plus propagation time P2 plus transmission time T3 is also 1.1 second plus propagation time P3. So it is going to be 3.3 seconds plus TP1 plus TP2 plus TP3. Okay, so this is the total time that is going to require to transmit this particular data packet. Now this happened in the case when we have not done any kind of packetization in this packet. When I'm saying packetization, that means divide the packet. When I'm saying packetization, that means divide the packet, divide the data packet in smaller units. Now do one thing, just note down all this information. Now let me do one thing, let me try and divide this data packets in the smaller units. Okay, so we have the same information, exactly the same information that we are using, but this time this is the original packet, which is having 100 bits here, 1000 bits here, and 100 bits here, where this 1000 bits is of data and this 100 bits is of header. Now for simplicity purposes, let us divide this packet into 5 smaller packets. Divide it into 5 smaller packets. Okay, so when I'm saying divide into 5 smaller packets, in that case I actually mean that dividing the data packet only. I mean dividing this part into 5 smaller units. So if we are going to divide this part into 5 smaller units, so every data here will be of 200 bits. So will be 5 small packets which will be of 200 bits. Again 200 bits. Again 200 bits. Then again 200 bits. And the last also 200 bits. So we have 5 small packets of 200 bits each. Assuming that this is the data packet 1, D1, this is D2, this is D3, this is D4, and this is D5. Okay. Now if you want to transmit this data packet through the network, now what will be the case is that this header will always remain same. This header will always be of 100 bits. The reason is the header contains the information which we require to send the data to the receiver. Okay, so that information can be the address, okay, of which can be destination address as well as the receiver address. Destination address as well as the receiver address. Okay, now if let us say this is the sender and this is the network, again the same network, and this is the receiver. Now this time, instead of transmitting one single data packet, we have to transmit these 5 smaller packets, and size of every smaller packet will be of 300 bits. Every packet will be of 300 bits and will be having total of 5 smaller packets. So this time we'll be transmitting total of 1500 bits. Now remember that initially we were transmitting only 1100 bits. Now this time we are transmitting a total of 1500 bits. But this is a very interesting thing, is that even if we are transferring more data comparatively, but still the total time taken will be less. Maybe, I mean it can be less, that I'm going to prove that it will be less, but that is not true in every case, that might be less. Okay, so I'm just going to show this, how this transmission time will be less and what will be the benefit of this. But before that, we need to understand that what is the concept behind this, how this thing is working, and why this transmission time will be less. And the concept behind this is called as a pipelining. The concept is pipelining. We have already studied this pipelining concept in computer architecture and organization, but for the students who are studying this for the first time, let me elaborate you what is the pipelining concept. Okay, assuming that this is pipelining is originally designed by Henry Ford for the Ford Motors while they were creating a car. So what happens is, assuming that you want to create a car, now this car may be having multiple parts. It may be having engine, it may be having chassis, it may be having tires, it may be having paint, it may be having finishing or fittings, etc, etc. Now what generally used to happen is that generally when the company gets an order to create a car, so initially it goes to the first phase, assuming that these are the phases P1, P2, P3, P4 and P5. That means initially they'll give a car to the first phase P1, where the people are going to create engine for this particular car. So every phase is having some time that they're going to take. So assuming that the first phase takes 5 days, the second phase takes 4 days, this takes again 5 days, this also take 5 days, and this also taking 5 days. For simplicity purposes, let us assume this is also 5 days. So every phase is taking a total of 5 days. So initially the first phase will take 5 days, and then the car will go to the next phase where the chassis will be built, so it will again take 5 days, and next phase will be built where the tires will be taken care of, so it is again going to take 5 days, and the next is the phase 4 where the paint will be taken care of, it will be again taking 5 days, and then finishing will again take 5 days. So in total, if you want to build a car, so that is going to take a total of 25 days to build. Now what Henry Ford did is he done something called as parallelization. He made these phases parallel. That means instead of what people used to do is they used to create one single car. So one single car take these 25 days. People used to get one single car, and one single car used to take these 25 days. Then they move on and create the next car, then create a next car. But instead of this, what Henry Ford did is he parallelized, he given some parallel implementations of these phases. What he said is, instead of creating one car and then move on to the second car, let us do these phases parallelly. So what he did is, so this is representing the phases, okay. So this is the phase 1, this is the phase 2, then this is the phase 3, and then we have phase 4 and phase 5. So we have a total of 5 phases here, like this, okay. So the car 1, let us say we have the first car, which is a C1. So the car 1 will go to the phase 1. Now as soon as we have already built an engine for the car 1, this is the 5 days, this every one is showing 5 days. So for the first 5 days I'm going to create car 1, and then the car 1 will move on to the second phase, which is the chassis phase. In that case I'm going to put car 2 in the first phase. That means parallelly, when we are building a chassis for the car 1, some other team might be working on creating an engine for the car 2. This is the car 2, and then when the car 1 will move on to the third phase, which is building the tires, then the car 2 will be in the second phase, which is building the chassis, and the car 3 will be in the first phase, which is building the engine. And then again, when the car 1 will go to the third phase, fourth phase, then the car 2 will be in the tires, car 3 will be in the chassis, and car 4 will be in the engine. And then the car 1 will be here, car 2 will be here, car 3 will be here, car 4 will be here, and car 5 will be here. So after the end of this, after the first 25 days, first car will come, car C1 will come, okay. But after that, every 5 day the next car will come. For example, after this, even if you continue, then you will see that after this every car will come in next 5 days. So if let us say you want to make 20 cars, for 20 cars the first car will take 25 days, but all the other 19 cars is only going to take 5 days to finish. So in total, this is the total amount of time that is going to take. But in the first case, if you want to make 20 cars, then it is going to take 20 into 25, which is approximately equal to 500 days, which is a very, very big number. So what Henry Ford did is he said, instead of implementing one thing, instead of creating one single car and then move on to the second car, let us make cars in phases, and 2 phases can work parallelly. So if car 1 is in the second phase, and we can make car 2 in the first phase, and so on. So this is the concept of pipelining. I think you already know the concept of pipelining, but just for simplicity, I've explained you this concept. Now this concept of pipelining, actually it is also applicable on this concept of packetization. Now as I told you that without dividing this packet, it takes approximately 3.3 seconds plus propagation time for this entire data packets to travel to the receiver. But let us see, if we divide this entire data packet into smaller packets, then how this is going to help. Okay, so the next video we'll see how this is going to help when we divide this entire bigger data packet into a smaller packet of 5 units. Okay.